In this video, we're going to practice a couple ideal gas law problems. So here's one. Lungs. A very deep breath has about 6 liters of air capacity. I'm given on average. It kind of changes by person and body build, but as a general rule, that's pretty close. Well, we live near sea level, so it's generally about 1 atmosphere outside, and fairly quickly the gas inside you warms up to body temp. So we're going to say that air is about 310 Kelvin. When you breathe air, only about 20% of it is dioxygen. Most of the rest of the 80% is dinitrogen. There's a little bit of water and a little bit of carbon dioxide and a few other things in it. Oxygen is what we need to breathe to survive, though. And so the question is, in a single breath, how many moles of O2 did you actually breathe? And so see if you can solve that. Go ahead and pause here. Give it a shot and come back and we'll work through it. All right, if you gave it a shot, well, 20% of the moles are oxygen, which means if I know the moles, I just have to solve what 20% of it is. So what I need is the moles. I need to solve the moles that we breathe in with one breath. And so I need moles on its own. PV equals nRT. It's going to be pressure volume over RT is equal to N. I have to divide the RT on both sides. Well, my pressure, 1.0 atmospheres. My volume, 6.0 liters. My R value, 0.0821 atmospheres, liters, mole, Kelvin. And my temperature, 310 Kelvin. That's going to equal my moles, 0.2357 mole, 2 sig figs. That is my total moles. That is the moles of all the gas. The fact that I have a mix of gas doesn't change anything. Ideal gas law just cares about the moles. The different species are irrelevant. And so a mixture of dinitrogen and dioxygen behaves the same as a bunch of pure dinitrogen or a bunch of pure dioxygen. There should be this many moles of gas, regardless of what that gas is. And so I want 20% of that. So 0.2357 out of every 100 of it, I want 20 of them. So 20%, that times 0.2. 0.047149 mole of O2. So 0.047 mole of O2. In a deep breath, you get 0.047 moles of dioxygen. Now, if you're working out really hard, you might breathe deep and fast, but most of the time we're actually breathing pretty shallow. Most humans only cycle about 1.5 liters per breath. So we'd be seeing 1/4 of that. On top of it, you only breathe a couple times a minute. So realistically, you might be seeing about this much per minute. Times it by 60 for the hour, and times it by 24 for the day, brings in about 67.89 mole of O2 per day. So about 68 moles per day. In terms of the amount of oxygen we have to breathe, and realistically we breathe even less at night, so it's probably lower than this. You don't actually bring in that much dioxygen. We need it to survive and we need a constant stream of it. But the actual amount of O2 that we breathe is not terribly significant. Well, it's just critical, but it's not terribly large in amount, especially not on any given breath. Let's talk about a weather balloon. At launch, volume was equal to 100 liters, so we'll say 100.0. The pressure down here at sea level was about 1 atmosphere. The temperature was about 295 Kelvin. It's going to travel. That hot air balloon, weather balloon, it's going to drift up and up and up and up. And as it drifts up, it's going to get bigger and bigger and bigger. There's just less gas at higher elevation on the outside, so the outside pressure is more at sea level and less as you get higher up. And it's also colder the higher up you get. And so in our case, what we find is that the final volume, before it breaks, and they do burst eventually, before it bursts open and falls back down to C, we found that the final volume had gotten up to 198 liters. The temperature was 242 Kelvin. What I want to know is, what was that pressure? What was the pressure outside before the balloon exploded? Give it a shot, see if you can calculate it. Well, you'll find that your moles were 4.13. And a good weather balloon isn't going to leak, so we can assume that's probably our moles at the end. So 4.13. Which means if I want to solve for pressure, it's going to be pressure equals nRT over volume. And so if we solve for our pressure and our RT and volume, well, my moles, 4.13 mole, 0.0821 atmosphere liter mole Kelvin, and a temp of 242 Kelvin. My volume had gotten up to 198 liters. So what was my pressure? I'll find that my pressure was equal to 0.414 atmospheres, or rounding to sig figs, 41 atmospheres. The pressure outside had decreased. I'd gotten colder, so balloon would have tried to contract, but I'd also stopped pushing as hard on the outside, and that was actually greater change, and so the balloon got bigger. We almost doubled in volume because my pressure actually dropped to less than half. As the pressure decreased on the outside, well, my balloon was allowed to expand more until my inside pressure had decreased to that same lower outside pressure. And so we can actually solve what the pressure up in the atmosphere was by knowing the volume and the temp of that balloon just before it popped. What pressure must have been exerted on the balloon to get it to that size. So it's a little hard to pull off, but if you have a balloon that's fairly hot when you seal it, like you have it over boiling water, and so that it's at a certain size, and you seal it and you throw it in your freezer. Well, one thing you can do is that when you have it at a certain size of the boiling water, use a ruler and mark lines on it 1 inch apart. Throw it in your freezer, let it cool down. And when you pull it back out, it will have shrunk. It'll be smaller. And if you measure the distance between the dots, they're now less than 1 inch. The balloon gets smaller. Sometimes it's visually hard to see, and the markings can help. But the idea is we can solve the temperature of our freezer this way in theory, or at least it helps us. If you use the measurement and you were to take the circumference of your balloon, you could find its volume and things. We're just going to find temperature for a balloon that has gotten smaller. And so if we had an initial balloon that was 1.0 liters, pressure though today is a little bit different. Our pressure initial was 1.21 atmospheres. We have our temperature initial. It was up at 373 Kelvin. And there were some moles that were in it. I want to find temp final though. And so my final balloon, when we take it out, we find that it is 0.85 liters. My pressure has gone down a little bit. It's 1.18 atmospheres. I want to find my temperature final. And my moles final, assume there's no leak. They should equal your moles initial. So give this a shot. See if you can find that final temperature of the balloon. All right, if you're back, well, I want to find those moles. Moles are going to equal pressure volume over RT. And so we have 1.0 liters. We have 1.21 atmospheres. 0.0821 atmospheres, liters over mole Kelvin, and temp 373 Kelvin. My moles initial are going to equal 0.0395 mole. And so that should be my same as my moles final, 0.0395, realistically with 2 sig figs. So I have my moles final. I want to solve for my temp. Well, pressure volume over an R should equal my T. And so my pressure in this case has gone down to 1.18 atmospheres. My volume has gone to 0.85 liters. My moles, 0.0395. And my R value is still the same, 0.0821 atmospheres, liters, mole Kelvin. All that should equal my temp final. I find that my temp final is 309.2 Kelvin. Now at first you're like, hey, wait a minute. That's definitely colder. 373 down to 309. And so taking it out of our hot source, it definitely cooled down and shrunk the balloon. However, 309 Kelvin is actually quite warm. I must have not thrown it in my freezer. Clearly, it's not below freezing, or down near it even. 273 is 0 Celsius. So this is, at best, room temperature, a room temp on a hot day. And so whoever was doing this experiment clearly didn't put our balloon in the freezer, but it did take it out of the heat source. So our balloon had to get a lot smaller because its temperature had gone down. And so this is a set of examples where we can take information and solve the ideal gas law, whether that's an odd situation of a balloon that was hotter and it cooled down, whether that's an expanding weather balloon that actually pops like they all do eventually and falls back to Earth, or whether that's looking and investigating how much oxygen is actually in your breath. How much do we use? We breathe continuously. We never really kind of add it up. But what is the oxygen content you require per day? And while you might breathe 68 moles of O2 per day, you actually don't use all of it. On any given breath, you probably use about maybe a fifth of it. Like there's a reason you can have a rebreather that scrubs carbon dioxide out of things. We don't actually use most of the dioxygen per breath. So realistically, you use way less than 68 moles of O2 in a day. There's a few examples